欢迎大家继续回到我们的频道。上期视频我们介绍了人工智能之父 Hinton 在今年年初接受采访的视频。今天我们继续给大家带来最新的 Hinton 在接受麻省理工技术评论的一个采访视频。Hinton 是最早研究机器学习以及 AI 的一批科学家，也是最早发现反向传播算法的科学家。在 AI 发展最艰难的时刻，也是一直致力于 AI 的最新技术研究。前段时间呢 ，Hinton 从 Google 离职，并提醒大家要当心 AI。那么本期采访视频 ，Hinton 也谈到了他为什么从谷歌离职，对自己所做的 AI 技术研究有没有过后悔，以及为啥要站出来警醒世人要警惕 AI， 还表达了自己的担忧。他表示，他最大的担忧便是，很大可能性上，人类只是智慧演化过程中的一个过渡阶段。想要知道为啥 Hinton 有这样的担忧，我们一起看完采访视频吧。为了方便大家观看采访视频，我已经将视频字幕翻译成中文，并进行了内容分段。本期视频一开始聊到了 Hinton 从谷歌离职的原因。Hinton 表示自己年事已高，想告老还乡，并且大语言模型已经严重超出了他的想象，改变了他对机器学习的看法。紧接着 Hinton 用一个例子说明了什么是反向传播算法，然后解释了大语言模型为啥可怕，因为大语言模型的链接数量已经远远超出了想象，像 GPT-4 这样的模型几乎比任何人知道的都要多得多得多，以及为啥他会感到恐惧。即使 AI 很可怕，但 AI 的研究不会轻易终止，除非几个重要的国家能够达到像核武器那样的恐怖平衡，否则任何一方暂停研究都是不切实际的。文字方面的大语言模型可能见顶，但是多模态如照片和视频等等都还有很大的发展空间。 AI 的训练数据是人类提供的，换言之 AI 只会在人类给它的知识边界中自学。那为什么会担心 AI 会颠覆人类呢？ Hinton 解释说，有迹象表明 AI 已经学会了推理。那么这就是本期采访视频的一个大致的概括，大家可以根据自己的喜好来选择观看哦。
Hi everyone, welcome back, hope you had a good lunch. My name is Will Douglas-Heaven, Senior Editor for AI at MIT Technology Review, and I think we'd all agree there's no denying that generative AI is the thing of the moment. But innovation does not stand still, and in this chapter we're going to take a look at cutting-edge research that is already pushing ahead and asking what's next. But starting us off, I'd like to introduce a very special speaker who will be joining us virtually. Geoffrey Hinton is Professor Emeritus at University of Toronto and, until this week, an engineering fellow at Google. But on Monday, he announced that after 10 years, he will be stepping down. Geoffrey is one of the most important figures in modern AI. He's a pioneer of deep learning, developing some of the most fundamental techniques that underpin AI as we know it today, such as backpropagation, the algorithm that allows machines to learn. This technique is the foundation on which pretty much all of deep learning rests today. In 2018, Geoffrey received the Turing Award, which is often called the Nobel of Computer Science, alongside Yann LeCun and Yoshia Bengio. He's here with us today to talk about intelligence, what it means, and where attempts to build it into machines will take us. Geoffrey, welcome to MTech.
Thank you.
How's your week going? Busy few days, I imagine.
Well, the last 10 minutes was horrible because my computer crashed and I had to find another computer and connect it up.
And we're glad you're back. That's the kind of technical detail we're not supposed to share with the audience. But
Okay.
it's great you're here. Very happy that you could join us. Now, I mean, it's been in the news everywhere that you stepped down from Google this week. Could you start by telling us why you made that decision?
Well, there were a number of reasons. There's always a bunch of reasons for a decision like that. One was that I'm 75 and I'm not as good at doing technical work as I used to be. My memory's not as good, and when I program, I forget to do things. So it was time to retire. A second was, very recently, I've changed my mind a lot about the relationship between the brain and the kind of digital intelligence we're developing. So I used to think that the computer models we were developing weren't as good as the brain. And the aim was to see if you could understand more about the brain by seeing what it takes to improve the computer models. over the last few months, I've changed my mind completely. And I think probably the computer models are working in a rather different way from the brain. They're using backpropagation, and I think the brain's probably not. And a couple of things have led me to that conclusion, but one is the performance of things like GPT-4.
So I want to get on to the performance of GPT-4 very much in a minute, but let's go back so that we all understand the argument you're making, and tell us a little bit about what backpropagation is. And this is an algorithm that you developed with a couple of colleagues back in the 1980s.
Many different groups discovered backpropagation. The special thing we did was used it and showed that it could develop good internal representations. And curiously, we did that by implementing a tiny language model. It had embedding vectors that were only 6 components, and the training set was 112 cases. But it was a language model. It was trying to predict the next term in a string of symbols. And about 10 years later, Yoshua Bengio took basically the same net and used it on natural language and showed it actually worked for natural language if you made it much bigger. But the way backpropagation works, I can give you a rough explanation of it. People who know how it works can sort of sit back and feel smug and laugh at the way I'm presenting it. Okay, because I'm a bit worried about them. So imagine you wanted to detect birds in images. So an image, let's suppose it was a 100 pixel by 100 pixel image. That's 10,000 pixels, and each pixel is 3 channels, RGB. So that's 30,000 numbers, the intensity in each channel in each pixel, that represents the image. And the way to think of the computer vision problem is, how do I turn those 30,000 numbers into a decision about whether it's a bird or not? And people tried for a long time to do that, and they weren't very good at it. But here's a suggestion for how you might do it. You might have a layer of feature detectors that detects very simple features in images, like, for example, edges. So a feature detector might have big positive weights to a column of pixels, and then big negative weights to the neighboring column of pixels. So if both columns are bright, it won't turn on. And if both columns are dim, it won't turn on. But if the column on one side is bright and the column on the other side is dim, it'll get very excited. And that's an edge detector. So I just told you how to wire up an edge detector by hand, by having one column of big positive weights and next to it one column of big negative weights. And we can imagine a big layer of those, detecting edges in different orientations and different scales all over the image. We'd need a rather large number of them.
And edges in an image, you mean just sort of lines, sort of edges of a shape?
A place where the intensity changes from bright to dark. Yeah, just that. Then we might have a layer of feature detectors above that detect combinations of edges. So, for example, we might have something that detects 2 edges that join at a fine angle like this. So it'll have a big positive weight to each of those 2 edges. And if both of those edges are there at the same time, it'll get excited. And that would detect something that might be a bird's beak. It might not, but it might be a bird's beak. You might also in that layer have a feature detector that would detect a whole bunch of edges arranged in a circle. And that might be a bird's eye. It might be all sorts of other things. It might be a knob on a fridge or something. Then in a third layer, you might have a feature detector that detects this potential beak and detects the potential eye and is wired up so that it'll like a beak and an eye in the right spatial relation to one another. And if it sees that, it says, this might be the head of a bird. And you can imagine if you keep wiring like that, you could eventually have something that detects a bird. But wiring all that up by hand would be very, very difficult, deciding on what should be connected to what and what the weight should be. And it would be especially difficult because you want these sort of intermediate layers to be good, not just for detecting birds, but for detecting all sorts of other things. So it would be more or less impossible to wire it up by hand. So the way backpropagation works is this. You start with random weights. So these feature detectors are just complete rubbish. And you put in a picture of a bird, and at the output it says like 0.5, it's a bird. Suppose you only have birds or non-birds. And then you ask yourself the following question. how could I change each of the weights in the network, each of the weights on connections in the network, so that instead of saying 0.5, it says 0.501 that it's a bird, and 0.499 that it's not. And you change the weights in the directions that will make it more likely to say that a bird is a bird, and less likely to say that a non-bird is a bird. And you just keep doing that. And that's backpropagation. And backpropagation is actually how you take the discrepancy between what you want, which is a probability of 1 that it's a bird, and what it's got at present, which is a probability of 0.5 that it's a bird, how you take that discrepancy and send it backwards through the network so that you can compute for every feature detector in the network whether you'd like it to be a bit more active or a bit less active. And once you've computed that, if you know you want a feature detector to be a bit more active, you can increase the weights coming from feature detectors in the layer below that are active, and maybe put in some negative weights to feature detectors in the layer below that are off, and now you'll have a better detector. So backpropagation is just going backwards through the network to figure out for each feature detector whether you want it a little bit more active or a little bit less active.
Thank you. I can assure you there's no one in the audience here that's smiling and thinking that was a silly explanation. So let's fast forward quite a lot to, that technique basically performed really well on ImageNet, and we had Joel Pino from Meta yesterday showing how far image detection had come, and it's also the technique that underpins large language models. So I want to talk now about this technique, which you initially were thinking of as almost like a poor approximation of what biological brains might do,
yes,
has turned out to do things which I think have stunned you, particularly in large language models. So talk to us about why that sort of amazement that you have with today's large language models has completely sort of almost flipped your thinking of what backpropagation or machine learning in general is.
So if you look at these large language models, they have about 1 trillion connections. And things like GPT-4 know much more than we do. They have sort of common sense knowledge about everything. And so they probably know 1,000 times as much as a person. But they've got 1 trillion connections and we've got 100 trillion connections. So they're much, much better at getting a lot of knowledge into only 1 trillion connections than we are. And I think it's because backpropagation may be a much, much better learning algorithm than what we've got.
Can you define?
And that's scary.
Yeah, I definitely want to get onto the scary stuff. But what do you mean by better?
It can pack more information into only a few connections.
Right.
We're defining 1 trillion as only a few.
Okay. So these digital computers are better at learning than humans, which itself is a huge claim. But then you also argue that that's something that we should be scared of. So could you take us through that step of the argument?
Yeah, let me give you a separate piece of the argument, which is that if a computer is digital, which involves very high energy costs and very careful fabrication, you can have many copies of the same model running on different hardware that do exactly the same thing. They can look at different data, but the model is exactly the same. And what that means is, suppose you have 10,000 copies. They can be looking at 10,000 different subsets of the data. And whenever one of them learns anything, all the others know it. One of them figures out how to change the weight so it knows its data, it can deal with its data. They all communicate with each other, and they all agree to change the weights by the average of what all of them want. And now, the 10,000 things are communicating very effectively with each other so that they can see 10,000 times as much data as one agent could. And people can't do that. If I learn a whole lot of stuff about quantum mechanics, and I want you to know all that stuff about quantum mechanics, it's a long, painful process of getting you to understand it. I can't just copy my weights into your brain, because your brain isn't exactly the same as mine.
No, it's not.
It's younger.
So we have digital computers that can learn more things more quickly, and they can instantly teach it to each other. It's like, people in the room here could instantly transfer what they had in their heads into mine. But why is that scary?
Well, because they can learn so much more, and they might take an example of a doctor, and imagine you have one doctor who's seen 1,000 patients and another doctor who's seen 100 million patients. You would expect the doctor who's seen 100 million patients, if he's not too forgetful, to have noticed all sorts of trends in the data that just aren't visible if you've only seen 1,000 patients. You may have only seen one patient with some rare disease. Mm-hmm. The other doctor who's seen 100 million will have seen, well, you can figure it out how many patients, but a lot. And so we'll see all sorts of regularities that just aren't apparent in small data. And that's why things that can get through a lot of data can probably see structure in data that we'll never see.
But then take me to the point where I should be scared of this, though.
Well, if you look at GPT-4, it can already do simple reasoning. I mean, reasoning is the area where we're still better. But I was impressed the other day at GPT-4 doing a piece of common sense reasoning that I didn't think it would be able to do. So I asked it, I want all the rooms in my house to be white. At present, there's some white rooms, some blue rooms, and some yellow rooms. And yellow paint fades to white within a year. So what should I do if I want them all to be white in 2 years' time? And it said, you should paint the blue rooms yellow. That's not the natural solution, but it works, right?
Yeah.
That's pretty impressive common sense reasoning of the kind that it's been very hard to get AI to do using symbolic AI. Because it had to understand what fades means. It had to understand about temporal stuff. Mm-hmm. And so they're doing sort of sensible reasoning with an IQ of like 80 or 90 or something. And as a friend of mine said, it's as if some genetic engineers have said, we're going to improve grizzly bears. We've already improved them to have an IQ of 65 and they can talk English now. And they're very useful for all sorts of things. But we think we can improve the IQ to 210.
I mean, I certainly have. I'm sure many people have had that feeling when you're interacting with these latest chatbots, sort of hair on the back of the neck, sort of uncanny feeling. But, when I have that feeling and I'm uncomfortable, I just close my laptop. So,
yes, but these things will have learned from us by reading all the novels that ever were and everything Machiavelli ever wrote, that how to manipulate people, right? And if they're much smarter than us, they'll be very good at manipulating us. You won't realize what's going on. You'll be like a 2-year-old who's being asked, do you want the peas or the cauliflower? And doesn't realize you don't have to have either. Mm-hmm. And you'll be that easy to manipulate. And so even if they can't directly pull levers, they can certainly get us to pull levers. Mm-hmm. It turns out if you can manipulate people, you can invade a building in Washington without ever going there yourself.
Very good. Yeah, so is that, I mean, if there were, okay, this is a very hypothetical world, but if there were no bad actors, people with bad intentions, would we be safe?
I don't know. We'd be safer than in a world where people have bad intentions and where the political system is so broken that we can't even decide not to give assault rifles to teenage boys. If you can't solve that problem, how are you going to solve this problem?